In this video, we're going to go over acyl group transfer reactions, esterification, thioesterification, and amidation reactions. These reactions, esterification, thioesterification, and amidation reactions, are collectively known as acyl group transfer reactions, where an acyl group is the RC double bonded O part of the functional group. Transferase enzymes are the major class of enzymes that catalyze acyl group transfer reactions in cells. So this is an overview of the different acyl group transfer reactions. The acyl group is highlighted in yellow. We have esterification. We have a carboxylic acid and an alcohol reacting together, and it forms an ester and water, esterification. You have a carboxylic acid and a thiol reacting together, and you get a thioester, and it's called a thioesterification reaction. And you have a carboxylic acid and an amine reacting together. You get an amide or amide and water, and it's an amidation reaction. So esterification reactions are reactions of carboxylic acid with an alcohol to produce ester and water. Thioesterification reaction is the reaction of carboxylic acid with a thiol to produce a thioester and water. A thioester is a functional group that's analogous to an ester, except the bond to the carbonyl carbon is SR instead of OR. So it's the same thing as an ester, except this heteroatom bonded to the carbonyl carbon is an sulfur instead of an oxygen, hence the thio. Thioesters are common intermediates in biochemical reactions. So predicting the structure of the ester or thioester in an acyl group transfer reaction, first you're going to remove the OH group from carboxylic acid. You remove the hydrogen from the alcohol or thiol. You join the removed hydrogen and hydroxyl groups to form water, and then join the two atoms from which the OH and H were removed to produce a carbon-oxygen bond for an ester or carbon-sulfur bond for the thioester. Don't interpret these guidelines as the actual order in which bonds form or break. They're merely steps to help you arrive at the correct structure for the product. So you can see here, here's an example. We have carboxylic acid. We remove the OH group from the carboxylic acid and the hydrogen from the alcohol. We combine those to make water, and then the oxygen of the alcohol forms a single bond with the carbonyl carbon to make an ester. So to practice, what's the structure? First, if this was a thiol, this oxygen right here would be an S, and the only difference would be S right here, a sulfur atom right here for your oxygen instead of an oxygen. So for practice, what's the structure of the thioester formed in the following thioesterification reaction? So go ahead and pause the video, and then when you're ready, come back and we will work on it. So the first thing we're going to do is I'm going to draw the structure up until the carbonyl carbon for my product, because I know none of this changes, only the functional group part changes. Okay, now I know that the alcohol of the carbonyl, so this bond breaks, and the hydrogen bonded to the heteroatom, the sulfur, breaks. These two will combine to form water, and this sulfur will combine with the carbonyl carbon. So I'll have sulfur, and then whatever R group is bonded to this sulfur. So this is bonded to two carbons. plus water. So I just combined or created a new bond between the sulfur and the carbonyl carbon, and the OH group bonded to the carbonyl carbon and the hydrogen bonded to the sulfur combined to form water. So esters, esters are very fragrant, and to create an ester, you react alcohols with carboxylic acids and form an ester. So you can see here that this particular ester, the fragrance of this ester is orange. And then we have banana, apple, pineapple, and so forth. So to form an ester, you have a carboxylic acid plus an alcohol, the carboxylic acid part until the carbonyl stays the same. You break the bond between the carbonyl carbon and the OH. You break the bond between the H and the oxygen of the alcohol, and then you combine the two between the carbonyl carbon and the oxygen of the alcohol. So biological esterification reactions, fats are triesters or glycerol known as triacylglycerols or triglycerides. They are formed by 3 esterification reactions involving 3 fatty acids and 1 glycerol molecule, and they're catalyzed by transferase or enzymes. So you have a fatty acid, this part right here is just a long chain alkane, and then you have your carboxylic acid part. You have glycerol, which has 3 alcohol groups. You have 3 esterification reactions that are going to occur that are catalyzed by the transferase enzyme, and you have 3 molecules of the fatty acid. Each esterification reaction adds 1 fatty acid to the glycerol. It creates, makes that ester functional group. And then you get 3 molecules of water at the end. The 3 fatty acids may be the same or different and vary in length of their hydrocarbon chain. So you don't need 3 of the same fatty acids here. You can have 3 different fatty acids. You can have 2 of the same fatty acids and 1 different. It doesn't matter. But the overall reaction is going to be the same. 3 molecules of water are also produced in the reaction. Cholesterol esters. Our cells transport cholesterol in the form of cholesterol esters, which are formed in esterification reactions of cholesterol and a fatty acid catalyzed by transferase enzymes. So we have a fatty acid plus cholesterol. We have our alcohol group on cholesterol, our carboxylic acid group on our fatty acid. Through the catalytic reaction of transferase enzyme, we combine the two and make a cholesterol ester plus water. So to practice, the fragrance of pear is due to the presence of the ester shown below. Show how you would prepare this ester in the laboratory in an esterification reaction. So go ahead and pause the video, and then when you're ready, we'll come together and we will go through which reactants you need to make that ester as a product. So in order to make an ester, you need a carboxylic acid and an alcohol. Carboxylic acid involves the carbonyl, and the alcohol involves the carbonyl carbon. And the carbonyl carbon is involved with the carboxylic acid. The OR group is involved with the alcohol. So you're going to break the bond right here. This is the carboxylic acid. I just rewrote it, putting the OH. Then I'm going to have my alcohol just like this. So I have my oxygen here, this part. So this part becomes the carboxylic acid, and this part becomes the alcohol. So I add the H to make a hydroxyl group, and then I add an OH to make my carboxylic acid, and both of those make the ester. Amidation reactions. An amidation reaction is the formation of an amide from a carboxylic acid and a primary or secondary amine in the presence of a catalyst. Tertiary amines do not undergo amidation reactions because they lack nitrogen-hydrogen bonds. To predict the product of an amidation reaction, you first remove the hydroxyl group from the carboxylic acid functional group. Remove one hydrogen from the primary or secondary amine. You join the removed hydrogen and the hydroxyl group to form water, and you join the two atoms from which the hydroxyl group and hydrogen were removed to form the amide. So again, don't interpret these guidelines as the actual order to which the bond making and breaking occurs. It's just to help you predict the products. So we take out the OH from the carboxylic acid and one of the hydrogens from the nitrogen or from the amine. This becomes water. And then we we create a bond between nitrogen and carbon to form the amide. So for practice, write the Lewis structure of the amide formed in the reaction below in the presence of a catalyst. So go ahead and pause the video, and when you're ready, come back and we'll work on it. So the first thing that we're going to do is I know that we're going to break this carbonyl carbon bond and OH group bond. I'm going to rewrite the R group bonded to the carbonyl carbon and the carbonyl. Then I'm going to look at where my nitrogen is. And I have my nitrogen over here. I'm going to remove one hydrogen because this OH and the H together make the hydrogen or make the water. Make a new bond between carbon and nitrogen. Nitrogen is still bonded to one hydrogen. And then it's bonded to the rest of this molecule. So it's 1, 2, 3, 4 carbons. So I removed a hydrogen from the nitrogen, formed a bond between the nitrogen and the carbonyl carbon, and the hydroxyl group or the OH group from the carbonyl carbon and the hydrogen from the nitrogen combine to form water. So this is a transfer reactions overview. It goes over the type of the reaction. So amidation goes carboxylic acid plus an amine, forms an amide plus water. Esterification is carboxylic acid plus an alcohol, makes ester and a water. Thioesterification is carboxylic acid plus thiol, goes to thioester plus water. In summary, ester and thioesters are formed by reacting carboxylic acid with an alcohol or a thiol in the presence of a catalyst. The fragrance of an ester depends on the structure of the alcohol and carboxylic acid from which the ester was derived. Triacyl glycerols or triglycerides or fats are triesters of glycerol and 3 fatty acids. Amides are formed by reacting a carboxylic acid with a primary or secondary amine in the presence of a catalyst. Tertiary amines do not undergo amidation reactions because they lack nitrogen-hydrogen bonds.